Another intermolecular force, this is what's called London dispersion forces. So what we're going to have is, let's say we have element X bonding with element X. So both these elements have the same electronegativities. So there is not a positive, negative side going on. We would say that is a non-polar molecule. I didn't draw that very well, but a non-polar molecule. There's no positive, no negative side. But what we can see is when we look at the periodic table, what we see is that fluorine and chlorine and oxygen and nitrogen, those are all gases at room temperature. That's what the red means. Bromine is a liquid at room temperature, where iodine is a solid at room temperature. And you go, okay, well, what's going on there? What's going on? Why is that happening? Well, all of those are diatomic molecules. So fluorine bonded to a fluorine, bromine bonded to a bromine, iodine bonded to an iodine. Well, what the difference here, what's going to happen is that they're all non-polar, same electronegativity on both sides, but as you look once again, one shell, fluorine, 2 shells, chlorine, 3 shells, bromine, 4 shells, iodine, 5 shells. As you go down the periodic table, what you end up getting is bigger and bigger and bigger shells. And so what we say is that the bigger the electron clouds are, the more polarizable they are. And so they can form what we call temporary dipoles. And so what that means is that they will actually form these lopsided sharing, because these electrons are not really found in these rings. They're really not found in these locked in positions. Those are areas of high probability. Electrons are actually just kind of like scattered about and in these areas of high probability. But what can happen is the bigger the atom is, the more polarizable it is. And so what I mean by that is, imagine if we have ourselves a non-polar molecule right there, and I bring by a negative charge of some sort. Well, like charges repel, and so this can induce a dipole. We can actually induce a dipole. Well, that forms a temporary dipole. It's an induced temporary dipole. Well, what can that do? If it's sitting by another fluorine, well, then this now partially positive side would attract electrons over here. And so this side become partially negative. And then this side can become partially positive, and we could get some attractive forces there. We call those dispersion forces. There's a guy named London dispersion forces. You'll also hear these referred to as van der Waals forces, even though van der Waals forces is all the intermolecular forces. So these are dispersion forces between these. Well, fluorine in a big group doesn't really form very strong bonds. It's a small molecule, so it stays a gas. It's not very polarizable. But now you look at iodine, and iodine with its big shells, big giant shells. Well, now we bring a negative charge here, and now what we get is we get a big shift of electrons. And what does that result in? A bigger partial negative and a bigger partial positive, which then can induce another dipole inside of another iodine. These are strong London dispersion forces. In fact, they're so strong that this is stronger than water at room temperature. Water, hydrogen bonding, really polar, positive, negative, but it's a liquid at room temperature. Iodine's a solid at room temperature. And so what do we end up getting? We get a large London dispersion force, a large temporary dipole, because the bigger the cloud, the bigger it is, the more polarizable it is. Another good example is wax. Wax is C25H52 paraffin wax, big giant non-polar molecule, but it's a solid at room temperature. All right, it's a big solid room temperature. It's very polarizable. Methane, on the other hand, look at methane. It's a gas at room temperature. Methane is a gas at room temperature, but I attach to it an area of negativity right there, a little hydroxyl group, and all of a sudden it's methanol. That's alcohol. It's a type of alcohol. If I put on another carbon here, this is ethane, but if I attach myself that's alcohol. That's what people think of as drinking alcohol. And so that's all there is to it. Anyways, back to your London dispersion forces. One of the really peculiar things about it is that typically, like iodine doesn't go through a melting stage. It sublimes, which means it goes from a solid to a gaseous state. And so one of the things we look at is that if this guy is inducing this guy, so this was non-polar, but now the black, shows polarity, and it's induced this guy to become polar. When they vibrate and move away from each other, that inducement goes away and they lose attractive forces. So they go from a solid to a gas.